let's get started. So, close that. Get back to OneNote. All right, so this week, welcome to Recitation. And let's talk about, we're going to just talk about some of the exam logistics first. Let me grab my notes. So, what's on the exam? We're going to look at Chapter 8. So, except 8.6 through 8.8. So, what's in 8.6? 8.6 is like some circuit stuff, which you cover in Physics 151, apparently. And 8.7 is what I covered last week. It's an optional section. And 8.8 is also an optional section as well. So you can read those if you want to. They might help you a little bit with like solving some of the problems, but like they're not going to be like explicitly like you need to know these for the exam. Okay, so that's Chapter 8. And then Chapter 9, we're going to be covering 9.1 through 9.5. And 9.5 is what Davi introduced yesterday with the defective matrices, and it's a huge can of worms that I was hoping he wouldn't open up, but now we have to talk about it. I'm not going to talk about it in recitation because it wasn't planned for Wednesday. So that's what's going to be on the exam. Any questions? It's also not written yet, and I'm going to help write it, so we'll see how it goes. Actually, after this recitation, I'm just going to go sit down and try to think of some problems. All right, so anything else? Yeah, I got a review session, right? A1 at 4 p.m. today. And that'll be recorded, like always. Okay. Any questions? So let's get started. So I'm not going to cover Chapter 8.5, and I'm going to encourage you to just read Recitation 10 from spring 2018. So there are a few notes there. Essentially, it's just a bunch of vocab, and I think I do an okay job with the notes in that section, essentially just summarizing what the important vocabulary is. All right, so let's jump into the first topic for today, which is reduction of order. So this is 8.9. Just going to make sure I'm recording. Okay, cool. So reduction of order, what is it? It's a method of solving differential equations. And let me get my sheet aligned. So here's the idea. The idea is that reduction of order, we reduce a second order differential equation or an nth order differential equation into an n-1th order diffeq. So usually, right, we've been dealing with like second order differential equations pretty much this entire class. We would reduce a second order into a first order diffeq. Okay, so that's the idea. So when do you use it? There's really three cases when you're going to use it, and two of them get paired together a lot. So the first case we use reduction of order is when we have non-constant coefficients. On our diffeq. All right, so we don't have like any method of solving non-constant coefficient diffeqs except for reduction of order. So the second condition then is going to be you're given a solution to the diffeq. All right, so again, these two get paired together a lot because, I mean, if we don't know how to solve non-constant coefficient diffeqs, then you have to use reduction of order, and a prerequisite to using reduction of order is that you have a solution to this to the diffeq. So if you're given a solution, you probably should use reduction of order. Okay. So that gets paired a lot, and then the third one is if just the right-hand side looks nasty. So what does that mean? If you have like ln's or like you have like 1 over x squared on the right-hand side, can't really deal with that. If you have, let's see, what I'm trying to say. Yeah, if it's a constant coefficient diffeq, you can use the 8.7 method, which I covered last week. But usually what happens is that you'll use differentially reduction of order to get rid of those bad-looking diffie-Qs. So this is what I'm going to do today. This is what I did on Wednesday. So if you have a friend in the Wednesday class, you can look at what they have for their notes there. Okay, so how do we solve this? So let's look at an example. And it's the following. All right, we have this differential equation, x squared y double prime minus 3xy prime plus 4y is equal to 8x to the fourth. All right, and you're going to see that it has non-constant coefficients because it has the x squared and it has the minus 3x term, and you're given an initial solution. You're given that y1 is equal to x squared. Okay, so how do we proceed? Step one is, or actually I'm going to call it step 0. Step 0 is the following, is to find a solution to the diffie-Q if not given one. All right, so I'm going to include it here because on a Wednesday we actually had to do this, and this almost always means find a solution to the homogeneous. Okay, so most of the time, if you have like a nasty looking right-hand side and you can find the homogeneous solution, then you would find the homogeneous solution and then you would use one of the two homogeneous solutions in the reduction of order step, which is step 1. So step 1 is to guess y of x. Okay, and this is different, right? Because previously we haven't been guessing y of x, we've been guessing the particular solution, yp of x. But here we're guessing the actual entire general solution. Okay, so what is y of x? It's okay. So we always guess that y of x is equal to y1 of x times u of x. All right. So y1 of x is just any solution that we're given, or any homogeneous solution that you solve for, and the u of x is the unknown that we want to care about. All right. So u of x is this big unknown to this problem. Okay, so step 2, we're going to plug in y of x into, and okay, skip a line for step 2 because I need to add something in step 1. We're going to plug y of x into the original diffie-Q, and in our case above, right, y1 was x squared, so this is x squared u of x. That's the part for that. So y1, so y of x in our case is x squared u of x. Okay, now we want to plug in y of x into the original differential equation. So if you look at the original differential equation up here, right, you'll notice that we have y double prime, y prime, etc. So we need to take these derivatives. Okay. So to take these derivatives then, so we have y of x, so now we need to take the derivative of y prime of x. And, okay, so you got x squared u of x. You need to find y prime of x. So you have two functions of x, like, for y, which means we use the product rule. Right, because you have x squared u of x. So y prime of x is going to be, if you take the derivative of the x squared term, you get 2x u of x plus x squared u prime of x. Okay, and now y double prime of x, what does that equal to? So now you got to take the derivative of this first doodad which is 2u to x plus 2x u prime of x. All right, and now you got to take the derivative of this second guy, which is 2x u prime of x plus x squared u double prime of x. Okay, any questions? Is everyone okay with all the steps up to here? Yeah, Jade.
When you're vacuuming the solution,
Yeah.
you said take the homogeneous. You mean like a portion of it or like the entire?
So for a second order homogeneous, right? How many solutions will you get?
You get like 2 terms.
You get, yeah. So you get like C1 times something and C2 times something, right? So you just take one of the two without the constant. Yeah. Because we didn't have a constant here, right? And either one works. It doesn't matter. So let's say you had like x. Let's say you had like e to the x and x e to the x, right? Obviously, the e to the x term will be easier to use, so you use that one. Kendo, do you have a question, or are we good? Okay. So, all right. So now, right, we have our original diffq, which was x squared y double prime minus 3x y prime plus 4y is equal to 8x to the fourth. Okay, so now we want to plug these in, but before we plug them in, we need to take advantage of the big tip. All right, and this is where we can simplify our algebra somewhat. So, right, the entire idea of reduction of order, right, was to reduce our diffq into like an order below it, right? So we want to take our second order differential equation, we want to reduce it to a first order differential equation. Well, if we just blindly plug in y, y prime, and y double prime, you're going to see that we're going to result in another second order differential equation, right? Because instead of just having y's, now we call them u's, and nothing changed, right? So what happens is that the u's, when you plug them in, just the u terms will cancel out. So u of x terms will cancel out. Always. All right? So what does that mean? It means that we can just treat as if we never had u of x terms. All right? It'll always end up being 0. So we can treat u of x terms as being 0. Okay, so we just don't plug those terms in. So what does that mean? So we have x squared, right? Well, y double prime, I'm not going to plug in this u of x term here. I'm just going to plug in everything else. All right? And so what is that? That's 4x u prime of x. So I'm going to combine the middle two terms. Plus x squared u double prime of x. Okay? And then minus 3x times, now I have to multiply by y prime, but I'm going to ignore the 2x u to the x, 2x u of x term. I'm just going to multiply by x squared u prime of x. Okay? And then lastly, right, the last term is really plus 4y, but what is my y term? My y term is x squared u of x, right? So it has a u of x term in it, but we're going to treat that as 0. And then that's equal to the right-hand side, 8x to the fourth. Okay, I'm going to make a little bit of a notation change here. I'm going to drop the of x's. So we're just going to have a u prime, u double prime without those parentheses. So now, what is this? This is 4x cubed u prime plus x to the fourth u double prime minus 3x squared u prime is equal to 8x to the fourth. Right, so here's a notation change. U prime is really like u prime of x. All right, and then we'll simplify this a little more. Now you get so x fourth u double prime. So you want the u double prime term or the highest order derivative term to be leading. So I'm going to make that out in front, and then these other terms cancel out a little bit. So now you just get x. Oh, this should be x cubed. And then so now you get x cubed u prime. And that's equal to 8x to the fourth. Okay? So this is a first order differential equation. And why is it a first order differential equation? Well, it kind of looks like if we replace u, like if we let u prime equal w, then this is really x to the fourth w prime plus x cubed w. Okay, so this is actually a first order differential equation. So then step 3 is to solve the first order diffq. All right, so that is then x fourth u double prime plus x cubed u prime is equal to 8x to the fourth. Right? And so how do we solve first order differential equations? If you remember, a few weeks ago we did or in class, you guys did the integration factor thing, right, to solve first order diffqs. And so that's what we're going to have to do here. So what we need to do is we need to make this term in front of 1. And to do that, we're going to divide the entire thing by x to the fourth. All right, so we just divide that top equation by x to the fourth, and we get u double prime plus 1 over x. U prime is equal to 8. All right, here we need to use the integration factor. All right, and if you remember what the integration factor is, it's going to be e to the integral of whatever the heck is in front of the u, in front of the u prime. So it's the plus 1 over x. Okay, so it's e to the integral of 1 over x. In our case, that's going to be e to the ln x, right? The integral of 1 over x is ln x. And then the e and the ln's kill each other, so now that's just x. Okay, so now what do we do? Now we multiply the entire thing by the int factor. All right, so we multiply the entire thing by the integration factor. And so now what do we get? I get x u double prime plus u prime is equal to 8x. This right-hand side is always equal to d dx of the integration factor times u prime. All right, always. And that's the entire reason why we even calculate the integration factor, is so we can have this left-hand side be this property. So now we get d dx of x u prime is equal to 8x. And now we want to get rid of that d dx, so we're going to integrate both sides. Okay. And now I have x u prime is equal to, the integral on the right-hand side is going to be 4x squared plus some constant of integration, c1. Okay, and if you watched last week's video, you're going to realize that last week we didn't need a constant of integration. And why was that? Well, here, remember what we're trying to solve for, right? We're trying to solve for the general solution, okay? And in the general solution, right, you have the homogeneous and you have the particular. Well, the homogeneous part has those unknown constants c1 and c2, right? So you have to be able to get c1 and c2 somehow. And the way we get it is through adding the constants of integration here. Okay? Yeah.
So how did you get from x double prime plus or xu double prime plus u into the
This is a totality right here. These two are equal to each other, right? Because because we can work it out on the side, but this is really d dx of x u prime of x. So you have to use the product rule on that, right? So that's u prime of x plus, what is it? You use the product rule, right? So I think xu double prime, right? And then you get the same thing. So that's the entire reason why we introduced that integrating factor. Okay, so now we got our C1. We have that constant of integration. So what was our goal? Our entire goal was to solve for this unknown u of x. Right? So now we have u prime almost completely isolated. So let's isolate it. All right, divide both sides by x. We isolate our u prime. And now one last integral on this u prime will get me u. So then I get u is equal to the integral of all this crap, that's 2x squared, plus c1 ln x. All right, and now we need to add the new constant of integration, c2. So that's u. And then step 4, we want to plug u back into the guess. So if we recall, y of x we guessed was equal to x squared times u of x. So now that's x squared times 2x squared plus c1 ln x plus c2. And so we get our general solution of y of x is equal to 2x to the 4th plus c1 x squared ln x plus c2 x squared. And that's our final answer. Yeah.
Do we ever check our guess? Like you said, it's a guess, right?
Yeah, so you can check your guess the following way, right? So you're told that x2 is a solution, or not x2, you're told that x squared is a solution, right? So that better show up in your final solution. It's right there. So, and if you like had to solve for the homogeneous, right? Like let's say you had to solve for a homogeneous and you plug the solution of the homogeneous to get the particular here, your homogeneous should show up. Any other questions? Okay, so I want to make one last note then about the reduction of order method. Reduction of order is fail-safe. All right, so if you have no clue what to do for a differential equation, like if we present something you just have no idea what to use, this always works. Okay, can't say the same thing about like, you know, method of undetermined coefficients, et cetera, et cetera. This will always work because it works for non-constant coefficients and it works for whatever the heck the right-hand side is. All right, as long as you can recover one of the solutions initially. Okay. Cool. Let's move on then. So chapter 9. Got systems of differential equations. And really it's linear differential equations, but we don't really talk about many of the other diff eqs. Okay. So what's going on is the following. Okay. So let's just jump straight into an example. Suppose you're given the following. x1 prime is equal to x1 plus 2x2, and x2 prime is equal to 2x1 minus 2x2. All right, so you notice that this first differential equation and the second differential equation, they're separate differential equations, but they're related in that they're reliant both on x1 and x2. Okay, so we have a system. All right, so and the reason why we're covering like chapters 9.1 through 9.5 for the exam is because really the first two sections of the chapter really don't do anything. So chapter 9.1 is telling you, hey, this is what a linear system is. Chapter 9.2 is realizing, okay, we can actually just put these guys into a matrix, right? So I can put the left-hand side into a column vector matrix. This right-hand side is really the coefficients in front of these x1s and x2s multiplied by x1 and x2, if you notice that, because it's a system. All right, so right there, we've covered two sections of the textbook in 2 lines. We can also notice now that, okay, so this is how the notation will be for the rest of the system section. This is like an x prime vector right here, right? So you have a vector of x1 prime, x2 prime. That's going to be equal to your coefficient matrix, which we call A, and then the x vector, which is the solutions that we're interested in. Okay, so we're interested in this x vector at the end. Okay, so how do we actually solve these systems? Well, we use the methods that we developed in Chapter 7. We're going to use eigenvalues, eigenvectors. Okay, so now we need to find eigenvalues and eigenvectors of what? Well, there's really only one matrix up there we can find an eigenvalue of, and it's the coefficient matrix. So, yeah, that's what we're going to use, right? Determine A minus lambda I. What is that? 1 minus lambda, 2, 2, negative 2 minus lambda. I'm going to assume you all still know how to do all of this, so we're going to breeze through this, like these steps pretty quickly. You're going to get the following characteristic polynomial, lambda plus 3, lambda minus 2. And so lambda is going to be equal to negative 3 and 2. Okay, all of this should seem very familiar. So now let's take the lambda equals 2 case. All right, and so A minus 2i looks like the following. So 1 minus lambda, negative 1, 2, 2, negative 4. Okay, and now we need to recover an eigenvector. So let's go back to our eyeballing basics. What's an eigenvector? Yeah, 2, 1. Okay, and then lambda equals negative 3, a plus 3i, you'll get 2, hold on, you get 4, 2, 2, 1. Right, and v2, what's an eigenvector? Yeah, 1, negative 2. Anything surprising here? No? Okay. All right, so now what's my general solution? So in general, for any eigenvalue eigenvectors, you're going to get x is equal to c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2 plus et cetera, et cetera, et cetera. Right? And this is the non-defective case. Okay, so in our case, what is this? Well, x is equal to, right, c1 e to the 2t, and then you need the eigenvector associated with 2t, so that's going to be 2, 1. All right, and then you add c2 e to the negative 3t times the eigenvector associated with negative 3t, and that's 1, negative 2. That's the solution, general solution. Okay. Sometimes it'll be written in the following way. Sometimes we're just gonna like combine them. So you're gonna actually get like 2c1 e to the 2t plus c2 e to the negative 3t, and then on the bottom it becomes c1 e to the 2t minus 2c2 e to the negative 3t. So sometimes it gets combined like this, and the only reason we do that is because then you see what like x1, x2 are. All right, so that's just the general solution for a system of differential equations. So what if we have an initial value problem? Okay, so let's take the same example as above. So same as above. All right, so the matrix is the same, but now you're given that x1 at 0 is equal to 1, and x2 of 0 is equal to 0. All right, so it's literally the same problem up here, except now you have this extra condition. X1 at 0 is equal to 1, x2 at 0 is equal to 0. Okay, so what does this really look like? Remember, so this really looks like, another way to write it is if they say x of 0 is equal to 1, 0. Right, because x1 is the top guy and x2 is the bottom guy. So that's another way we can present the initial value problem. Okay, so what do we do? There are two methods to do this. The first method is to x of t is going to be equal to e to the at times x0. All right. If you remember what e to the at is, that was the matrix exponential that I covered in recitation a few weeks back. Okay, so that's the first way you can calculate it. I'm actually not going to do this way. All right, method 2 is actually just to solve using x of 0. So up here, right, up here we have this guy. So we just plug in 0 for the t's. So you get x of 0 is equal to like 2c1 plus c2. And then the second row is c1 minus 2c2. And that's supposed to be equal to 1, 0. Okay, so now all we have is just a system of unknowns, 2 equations, 2 unknowns. And we have to solve for c1 and c2. So, okay, so this is really this augmented matrix 2, 1, 1, negative 2, and then 1, 0 from the right-hand side. And then we're going to do some weird reducing. I'm going to reduce the top guy to 0. Doesn't matter. All right. So you'll get 0, 5, 1, and then 1, negative 2, 0. So C1 is equal to, C2 is equal to 1/5, and C1 from the bottom you'll get is equal to 2/5. All right, so here are my coefficients. And yeah, so once you're done with those, right, you just plug these back all the way up in here. But we know the drill. Any questions? Okay, so these non-defective matrices, they're really not that bad. Defective matrices are pretty bad, though. And so, but we're not going to talk about them. Next thing we're going to talk about is another example. And in this example, we're going to get complex eigenvalues. Okay? So this is fall 2016, number 5. This is a final problem. And we have the following. So you're given the coefficient matrix A is 0, 1, 0, negative 1, 0, 2, 0, 0, 1. right? It's really an initial value problem, but we're not going to do that initial value part of it just to save some time. So let's just say find x prime is equal to ax. All right. This characteristic polynomial stuff, I believe you'll be able to handle it. I'll just give it to you. It's 1 minus lambda, lambda squared plus 1. Okay, so that means then lambda is equal to 1 and plus or minus I. All right, so we got lambda equals 1 plus or minus I. What do we do now? So, okay, so let's take a look at the lambda equals 1 case, right? Because that's going to be the easiest one to work with. Lambda equals 1, that's what? That's a minus I, which is negative 1, 1, 0, negative 1, negative 1, 2, 0, 0, 0. Okay, so what's an eigenvector? Looks like 1, 1, 1, 1. Okay, so 1, 1, 1 will work. Okay, so now we got to deal with the complex eigenvalues. Lambda equals I. So now we got a minus II. And if you remember, right, remember from chapter 7 when we did all this complex eigenvalue stuff, if we find one eigenvector, right, we can get the other one just by taking the i's and then just like negating them, right? So we're taking the complex conjugate of any like imaginary number that we get in our eigenvector. So here we'll get negative I, 1, 0, negative 1, negative I, 2, 0, 0, 1 minus I. Okay, so now we need to find an eigenvector v2. All right, the last row. What does the last row tell me? All right, the last row has this 1 minus I term inside of it, but there's nothing else to cancel it out. So it has to be 0, right? So the third entry must be 0. All right, so from there, then we just go row by row. From row 1, right, I need to make this dotted with this somehow equal 0. And we see that, okay, if I let this stay as negative I and make this somehow positive I and I add them together, I'll get minus I plus I, right? And that'll get me 0. And so then 1I, 0, that would work. Okay. And then the other eigenvector is going to be 1, negative I, 0. But we don't really care about this other eigenvector. I mean, it's fine if you just want to write it down, but it ends up not doing anything. Okay. So now what? So now we can write the general solution. And so now everything on the blackboard is relevant now. So if you want to look at the blackboard, that's where I'm going. So we want to find the other, we want to find the general solution, right? So the general solution is the following. X of t is going to equal to, well, okay, so this first eigenvalue is real, right? So we can just write that one down. That's going to be C1, e to the lambda, or e to the 1t, so that's just e to the t, times the eigenvector 1, 1, 1. Okay? But, all right, so don't copy this down. I'm just going to write it out and show you why something doesn't work. if we add in C2, e to the it, 1I0, right? Why doesn't this work as a solution? Yeah.
Could you reduce it further? Or like simplify?
Yeah, you can reduce it further, and the more simple thing would just be to say like you can't have i's in your final solution, right? You can't have imaginary numbers in your final solution when our initial coefficient matrix was just all real, right? So yeah, so we can't really do that. So what we have to do is we really have to just take a look at this guy. So let's erase that, save some space. So really, right, from lambda equals I case, we're going to get e to the it, it's the eraser, times 1I0. Okay, and since I have a 3 by 3 coefficient matrix, right, my general solution has to have 3 terms inside of it. So somehow, some way, I need to recover 2 solutions from just this guy. Does that make sense? All right, so how are we going to recover 2 solutions from this? We're going to abuse the fact that there's a real part and an imaginary part, okay? And so that's how we can get 2 linearly independent solutions. So we're going to do the following. E to the it, all right, times 1I0. E to the it is equal to cosine t plus I sine t. Right? And that's Euler's formula. We've been using it ever since 8.4. Now what I'm going to do is I'm going to factor out this 1I0 term into a real part and an imaginary part as well. So what does that look like? Well, you take all your real coefficients, which are 1, 0, 0, right? And then you add it to I times 0, 1, 0. Okay, so this term here, this is really just 1I0 written out with a real and imaginary part. So the next step is we're just going to FOIL them. Okay, so first is cosine t 1, 0, 0. Outer, okay, is going to be plus I cosine t 0, 1, 0. Inner plus I sine t 1, 0, 0. And then last, all right, so the last 2 terms, you get an I squared, which is negative 1, so you get negative sine 0, 1, 0. Oh, sine t. Okay. So you get negative sine t 0, 1, 0, and okay, so now what? So now to plug this in to these guys up here, what I'm going to do is I'm going to choose the real parts for one solution. I'm going to choose the imaginary parts for the other solution. Okay, so this first solution, C2, let's just make it the real guys. So it's going to be this cosine term, and then this negative sine term right here. All right, so now this is going to be cosine t 1, 0, 0 minus sine t 0, 1, 0. All right? So that's going to be one of the linearly independent solutions. And then the other linearly independent solution are the imaginary terms. Okay, so I'm going to plug the imaginary terms in for C3, except what do I have to do to the i's? Yeah, you got to just drop them, right? Because we can't have i's. So this is really C3 cosine t 0, 1, 0 plus I sine t 1, 0, 0. right? So I just took these guys, dropped the i's, and inserted them for my other solution. Yes. What?
You didn't take out the
Oh, I didn't take out the I. Oh, right. Thank you. Yeah, so that's just sine t. You can't have an I. So one way you can think about it, you can think about like the C3, like the constant term, like 8 the I. That's one way to think about it, but you just can't have the imaginary term in there at the end. All right, and then this is then the correct general solution. Okay, any questions? Yeah.
Did we use V3? The 1 minus I2?
1 minus.
You know how we had like V2?
Yeah, we didn't need V3. Right. I said V3 was like useless. Right. I was like, you can find it, but like it's not gonna do anything. It's because of how this cosine. It's because of how this e to the it expansion works. Right. You would have just had e to the negative it. Right. Because V3 corresponds to V3 is the eigenvector for lambda equals negative I. Right. And then if you did this expansion out here, you'd more or less get the same thing. Right. So what might happen is that what could happen is that this is now like the imaginary term. Like this could be like the imaginary term now, but like you'd still get the same solution. So yeah, so it doesn't affect the outcome. Yeah.
What's the difference between throwing out the i's at the very end, like what the difference, like throwing them out earlier when you could have just done it in your solution?
Where would you have thrown it
A
out?
little bit higher. Just like in the I don't know, V2, V3. Just,
Here?
well,
Well, how do you recover your sine and cosine terms? Well, I guess you can. Because of that. Why doesn't that work? It doesn't work because you wouldn't know if the cosine term or the sine term goes on top or the bottom. Right? Because what you would have like, you would end up here, right? But this thing wouldn't be foiled. It would just be 1, 1, right? And then you would have cosine plus sine, right? Because you would have this. Right? But now this is just equal to cosine t plus I sine t, cosine t plus I sine t. That's wrong. So you can't just do that. Okay, so yeah, you have to keep that I in till the very end. That's a good question though. Any other questions? All right. Well, this is pretty much it. The last thing we're going to have to talk about that I didn't have time to talk about today is the defective matrix case. I'll do that at the review session, and I'll update the practice problems as well to include some defective matrix cases. Those really are a pain in the ass to talk about. So that's that. Remember, review sessions at 4. One last thing. If you want practice with just finding eigenvalues and eigenvectors, or complex eigenvalues and eigenvectors, you can look at Recitation 12 from spring 2018. I think I dedicated half that recitation just to find eigenvalues, eigenvectors in the complex case. So you can use that as a resource. And again, for those of you that are going to show up this afternoon, I'll see you then. And office hours today, like usual. Monday, I might change my office hours, like extend them a little bit, and like add a different time of day. But I'll send an email about that as well.